In this lesson, we're going to take a look at problem solving with the ideal gas law. So we start off with the ideal gas law and just consider that a lot of this work is going to go into decoding the question. Because if we're going to go from all this text into this, then obviously there's going to be a lot of vocab that we have to break down. And of course, we want to keep an eye out for units too, but I wanted to use this particular example as a way of taking out that coding. So the pressure in an ideal gas is cut in half slowly while being kept in a container with rigid walls. Clues, clues, clues. In the process, 265 kilojoules of heat left the gas. How much work was done and what's the change in internal energy? Well, that sounds crazy because they told us about heat. That's the one thing that's explicitly stated, but everything else is implied. All right, so then let's just, lean into that. And it said heat left the gas, so left, right? Okay, so that means that Q, heat left the gas, so it's no longer available. If it's no longer available, then it's going to make our temperature go down. So that's a loss. So left equals loss. So this is going to be minus 265 kilojoules. But what's implied? This right here, container with rigid walls. So if the walls are rigid, then that means that the change in volume has to be equal to 0. So if there's no change in volume, and that's what we call, that's an isobaric process. I'm sorry, isovolumetric. And so it's implied that if delta V is equal to 0, then there can't be any work done. So the work done is equal to 0. So if the work done is equal to 0, then Q is simply equal to delta U. And so now we take a look at it. How much work was done? Was 0. And since if the work done is equal to 0, these two are equal to each other. So the change in internal energy is just equal to negative 265 kilojoules. And of course, the work done is equal to 0. So this is the answer to A, and this is the answer to B. And that's it. We didn't even have to do any math at all. It's all conceptual, but it started off by trying to break apart all the words. Pressure in an ideal gas is cut in half slowly. That didn't even apply. So it was just a red herring. All right, let's take a look at another one. Sketch a PV diagram of the following process. Now, a PV diagram, we'll just start off with it. The significance of a PV diagram is that every point will have a unique pressure and volume. And if it's got a unique pressure and volume, then that also means the temperature is unique to that location. Now, there might be a set of points that all have the same temperature, but that also means that each location on the PV diagram has a unique internal energy, which we would call state. So each point on our PV diagram It has a distinct temperature. Therefore, internal energy. And when we talk about energy, we usually mean states. And it is considered a unique state. And not state as in State of the Union, but state in the sense of condition. Okay, great. Well, let's start decoding now. And we'll do a quick read through first. So 2 liters of an ideal gas at atmospheric pressure, so that's 1 atm, are cooled at constant pressure. Oops, that's important. Yep, decoding to a volume of 1 liter. So 2 liters down to 1 liter. And then expanded isothermally. Whoa, so much, so dense, expanded isothermally back to 2 liters, whereupon, what the heck? Whereupon, that just means another step in our process. The pressures increase to constant volume until the original pressure is reduced. So I'm just counting that, and I see 3 separate movements on our PV diagram. So cooled at constant pressure. Okay, so that's 1. And then expanded isothermally back to 2 liters. So I see that as 2. And then whereupon, come on, man. The pressure is increased at constant volume. And so I see that as 3. So let's break them down into 1, 2, and 3. So here's what number 1 would look like on a PV diagram. And then we'll put them all together. Right, so here we go with our PV diagram. We're just going to sketch this out really quick and know that ultimately we're going to string all these together. But so cooled at constant pressure, that means the pressure doesn't change. And back to a volume of 1 liter. So we're going to go from 2 liters down to 1 liter at whatever this pressure is. So, and I'm going to put a little arrow to indicate the direction that we're going. Okay, so let's look at the next one. Same thing, PV diagram. Notice with the first one I don't know anything about. It's 1 atm, right? So I'm just going to go 1 atmosphere. Okay, so in the second one, it says pressure cooled at constant pressure. Wait, that's the first one. And then expanded isothermally back to 2 liters. So, so we left off at 1 liter last time, and we're going to go back to 2 liters, but we do it isothermally. So isothermally is sort of an inverse curve that looks like this. Now let's just remember, so constant pressure means that work done equals pressure times change in volume. And here with an isotherm, delta T equals 0. So that requires that the change in internal energy is equal to 0 during that process. Okay, good. And then 3, the pressures increase at constant volume until the original pressure is released. So all right, so for number 3, we have pressure and volume. We left off at 2 liters down low, and then it says the pressures increase at constant volume until the original pressure is reduced. So constant volume is going to look like this. So up here, we went from right to left, and then we swooped down, and now we're coming back to where our starting point is. So since it's constant volume, delta V is equal to 0, so work has to be equal to 0. Great, so now we're going to put them all together into one big PV diagram. And pressure. Okay, and here we go. So we went from here to here, then swooping down, and then back. So with a closed loop, we wind up back at the same temperature. A little sunshine slipping in there. Let's try and scoot out of it a little bit. Okay, great. So closed loop lands back at the same temperature. And if you're back at the same temperature, then that means for the entire loop, delta T is equal to 0. And so the change in internal energy is also equal to 0. All right, hang in there for one more, please. Okay, so here we go. We're going to have some unit considerations here. So we want to be mindful about that. And so I'm just going to make sure I have a unit converter up here, up and running. Again, if you want less non-unit conversions, I can certainly help you out with that. But let's just go ahead. I know that 1 liter, if we want SI units, then that would be cubic meters. So that means we'll multiply this times 10 to the minus 3. So that's a pretty easy conversion. And then I'm going to share my screen really quickly, and we'll convert these. We'll convert these pressures from atmospheres into newtons per square meter. So I'm going to share my screen. And we'll go out to a unit converter, which is right here. Okay, and then the unit we're trying to convert is pressure. And our base unit is pascals. I mean atmospheres, rather. Okay, and so 1.4. And we'd like to turn that into pascals. Okay, so 1.42 times 10 to the 5th. So I'm just going to write that down. And that's newtons per square meter, also known as pascals. And then the other number I want is 2.2. Okay, totally legit to do this on a quiz or test or homework. So 2.23 times 10 to the 5th. Okay, great. So I'm going to stop sharing my screen and we'll go back. Just a quick focus here. Okay, that looks pretty good. All right, now let's start decoding. Two-step process, heat flows out of an ideal gas at constant volume, so its pressure drops from 2.2 down to 1.4 atmospheres. So that's A to B. And then the gas expands at constant pressure from a volume of 6.8 to 9.3 liters. And then the temperature gets back to the original value. Oh, okay. All right, so the temperature at A equals the temperature at C. Okay, so for the path A to B, that's happening at constant volume. So I know the work done has to be equal to 0. That's implied. And I don't know the other two, but I do know that when we're going from B to C, the gas expands at constant pressure from 6.8 to 9.3, and then our temperature gets back to the original value. So there's a whole bunch of information that's there. So we know that those two are at the same temperature. So the overall change in internal energy should be equal to 0 if I add up these two. All right, that's probably helpful. Calculate the work done by the gas in the process. So going from A to B, no work's done. But going from B to C, then we do have work done, and here's how we calculate it. So A to B is isovolumetric, B to C is isobaric. So the work done equals pressure times delta V. Now, of course, you can see that we've already done this, 1.42 times 10 to the fifth. We've already have it in useful units. And the change in volume is going to be 9.3 minus 6.8 times 10 to the minus 3. Oops. All right. And don't forget the 10 to the minus 3 thing. Okay, let's bring in our calculator. And we'll take care of that. Okay, so 9.3 minus 6.8. Okay, and then we're going to multiply by 10 to the minus 3. A couple of different ways to do this. So I could do 10 raised to the minus 3 power, but here's a smarter way to do it. 1e minus 3. That's scientific notation for 10 to the minus 3. Right, that's what we were looking for. Times 1.42 E5. And that's 355. Okay. So we'll move that off and we'll fill in 355 here. Okay, now, if you like Sudoku, which is that game where you try and get numbers to line up, this is very much like Sudoku. So if I add up the total work done, I get 355. But this has to total up to equal 0. So that means the total heat, because remember, Q minus W equals that. So if that's 0 and that's 355, then I need something here so that when I subtract 355 from it, I get 0. So that's positive 355. I don't know this, and I don't know this, and I don't know, but that's about as far as I could go. Oh, sunlight's back. Okay. But it turns out we don't need to know those things because if we look at the different parts of the question, so A says total work. So that's 355 joules. B. They'd like to know the change in internal energy of the gas in the process. So that's just 0. Right. And let's see what's next. Change in internal energy, we already said is 0, because we wound up back at the same temperature, and then the total heat flow is 355. And that's it. So we didn't need to fill in these other things, but the table is quite useful because it helps keep your thoughts organized. In the next video, we're going to, kick us up to the next level.